So, now what we're going to do is we talked about all of these gas laws, and we want to understand a way to remember the relationship between pressure, volume, temperature, and even moles too. Charles Gay-Lussac's, Boyle's, and Avogadro's law. This equation up here called the ideal gas law will help us out significantly. And my AP chemistry students will tell you PIV-NERT, PV equals nRT, you always use when you deal with gases. It comes up over and over and over again. So, what do these variables represent? Of course, P is representing our pressure of the system. V, of course, is our volume. N is how much stuff is there, which is moles. And R is a thing we call the gas constant. T is temperature, of course. I'm just going to abbreviate it temp. But we also need to know the units that are used. We have to be very, 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 very careful to make sure we use the correct units. Otherwise, we will always get it wrong. So what Mr. Barron is doing right now is he's literally busting out his AP chemistry formula sheet. There are several different numbers for R, so it can become confusing sometimes. See the gas constant in the bottom right that I've pointed at with my pen? So see how they're all different numbers? They're all the same amount. The thing is that they're all being represented in different units. This top one's in joules per mole Kelvin. The second one's in liters, atmospheres moles Kelvin, torrs moles Kelvin, volt coulombs moles Kelvin. All right, we are only going to be using the 0.0821 number. That is it. So we're going to write that down as it is always 0.0821. And then the units that it is going to be atmospheres, moles Kelvin, but these need to be inverse. So you're putting them to the power of -1. I'm sorry if that's a little small up there. That means that they're on bottom whenever we write to the power of -1. Now what we're going to do is talk about the units. See how this is in atmospheres, moles Kelvin? That means my temperature has to be in Kelvin. Moles, well, that's already moles. Volume has to be in liters. Oops, I forgot a unit. I know there was a reason why I left space. Liters, atmospheres, moles Kelvin. I'm sorry about that, folks. So this volume is in liters, and the pressure is, of course, in atmospheres. All right, so why is the ideal gas law cool? I think it's cool because then you don't have to memorize what the relationship is in terms of whether it's direct or inverse. So I'm writing out PV equals nRT. P and V, do you guys see how these two are on the same side? Because they are on the same side, the relationship between them is inverse. Do you see volume and moles? See how they're on opposite sides of the equation? That means they're direct. And that makes sense because I just did the most awesome demonstration on the planet where I blew up a balloon by increasing the moles and my volume of the balloon got bigger. That was a direct relationship. One got bigger, the other one got bigger. So don't forget, direct is they both are changing in the same way, and in inverse, they're changing opposite. Any questions about that? Sweet. Now we're going to talk about something called the combined gas law. And the combined gas law allows us to predict how properties change for a gas. What we're going to do is we're going to move away from this. And then now we're done with PV equals nRT. Now we're going to use the combined gas law. So the combined gas law uses 1s and 2s instead of I's and F's, but they mean the same thing. So P1 V1 over T1 equals P2 V2 over T2. The 1s mean that's before the change. So all this stuff here is before the change. This is after the change. It allows you to predict how gases change. So I'm going to go back and imagine the Mr. Bird example. What I'm going to do is go back to the picture of Mr. Bird swimming, and we're going to use data to help us understand how that works with Mr. Bird swimming as soon as my computer is able to load it. So I'm going to switch back to my projector, and we're going to go back to Mr. Bird swimming. Wow, he's forever going to be on my podcast. That's awesome. So he's swimming, right? And what's happening is he starts diving. He goes deeper and deeper and deeper. As he goes deeper and deeper and deeper, what's increasing around his body? Pressure. Good. So let's write a problem. This is an example problem with Mr. Bird. He's swimming, the pressure increases from 1 atmosphere, which is air pressure at sea level, and of course we're talking about his lungs, and it's going to 2 atmospheres because he's diving. His lungs are 1 liter large. I don't know if that, no, that's not even close to real, but let's say his lungs are 1 liter. How, I mean, lungs are really just a balloon. How does their size change? Actually, I would argue that it's small. The reason why I'm guessing small, I don't know if, do I have an AP biology person here? I don't know, I'm guessing it's small. The reason I'm guessing it's small is just because, I mean, there's a lot of surface area within the lungs, and I don't know. I have no idea, actually. I have no idea if it's true. So anyhow, given information. We're going to break this problem down by isolating the numbers that were given to us. So the numbers that I was given were atmospheres going from 1 to 2. Because it's starting at 1 atmosphere, we write P1. It's going to 2 atmospheres, so we label that as 2 atmospheres. We have our volume, which is 1 liter. That's the volume before the change, so I'm going to write it as V1. Since I'm trying to figure out what it changes to, I'm going to write V2 equals question mark. Now here's the cool thing, is that like we already know that the volume of his lungs is going to get smaller because they're being squeezed, right? But this equation, the combined gas law equation, allows us to figure it out quantitatively. So our formula in this problem is going to be P1 V1 over T1 equals P2 V2 over T2. Rule number 1 for using this equation. Rule numero 1. Cross out the variable that's not changing. Cross out what is held constant. And the thing that's being held constant in this particular problem is the temperature. Because we don't have any information on it, and obviously his lungs are staying at the same temperature. We're all warm-blooded. Even if you go diving in a cold ocean, your lungs are still pretty much at 98 degrees Fahrenheit. So we don't need that variable, which means our equation is really just P1 V1 equals P2 V2. That's it. That's the only equation we have to use. There is a very important second rule. The very important second rule is only if we're working with temperature. All gas problems, all gas, I'm going to call them Q's, questions. All gas questions are in Kelvin. They have to be in Kelvin. Any questions about that? We don't have temperature in this problem, so we're okay. Now we're going to get to the work of this problem. I'm going to plug in my variables and solve for my unknown. In this particular problem, I have P1 as 1 atmosphere. So I'm going to write it down, plug it into my equation as 1 atmosphere, times the volume, which is 1 liter, equal to the pressure, which is 2 atmospheres, times the second volume, which is just V2. I'm going to leave it V2. Then I have to, of course, solve for V2, so I'm going to divide by 2 atmospheres on one side. In class, when I do it to one side, I have to do it to the other side. I just always like saying that. I don't know why. Make sure the units cancel out. These things totally cancel out. The ATMs cancel out, so it's 1 times 1 divided by 2, which is 0.5 liters. His lungs decrease in size by half. Now, of course, I chose a really simple problem. I'm going to pass out a worksheet. It has a lot more complexity to it, but it's the same type of concept. You have to use the combined gas law, and it allows you to quantitatively predict how a gas changes. Duh, Mr. Bird's lungs get squeezed. But now that we've solved this problem, we're going to look at how to use this equation or this one. There are 2 different equations that I've showed you for gases. This one, the one on the left, that one is for when a gas changes. Say I squeeze the gas, heat it up, or I increase or decrease its pressure. Whatever I do where it's a change. That's why the 1s represent before, the 2s represent after. I use the combined gas law. Notice the combined gas law does not have the N for moles, so you don't use this with moles. Or at least you can't study a change in moles with this equation. The one on the right is when there is no change for a gas. None at all. So an example of a problem dealing with PV equals nRT where there's no change for a gas. would be, say I had a gas that was at 2 atmospheres, and say I had it and it was 5 liters, and say I knew that the temperature was 50 degrees Celsius. And then I wanted to count how many moles of the gas there are. Well, what I would do is I'd plug these in. This is some gas and some balloon, and I don't know how many moles, and if I know the moles, I can figure out the molecules, but I do know its pressure, because I have a pressure gauge. I can measure its size, and I can measure the temperature. So what I do is I plug all of these numbers in. Of course, in every gas problem, no matter what, it is always got to be represented in Kelvin. You have to add 273 to figure that out. When you do that, then what you want to do is take this number, plug it in there. Then you want to take this number, plug it in there. You want to take this number, plug it in there. Because remember, this has to be in atmospheres, this has to be in liters, this is in moles, and the temperature, of course, is in Kelvin. Then you would have to rearrange your equation to solve for, we're solving for moles, so I'd move R and T to the other side, and N equals PV over RT. You just take these numbers, stick it in there, and don't forget, R is the 0.0821 number that I referred to earlier in this lecture. Now, a different type of problem. Say I have a problem where I'm dealing with a change in a gas. Say its volume is 2 liters, and say its temperature is 53 degrees Celsius, and say I heat up the temperature up to 80 degrees Celsius. And I want to know what the volume increases to. Well, the given information you'd want to label. This is before the change, that's after the change. The volume before is 2 liters. The temperature before is 53 degrees Celsius, but we want to represent that in Kelvin, so I would have to add 273. When I do that, then of course I get my answer, which is 326, I believe. And I know my final temperature is 80 degrees Celsius. Add 273, and that would be 353. Kelvin. So that is my volume. This is my initial temperature. That's my final temperature, which we call T1 and T2. Let's go to the formula. The formula that we're working with in this problem is P1V1 over T1 equals P2V2 over T2. The rule I told everyone is to cross out the variable we are keeping constant. In this case, we're changing the temperature, studying the volume change, but we don't have any information on pressure. Because we don't know anything on pressure, we can cross it out. And we're going to use V1 over T1 equals V2 over T2. I'm going to go ahead and use this formula and plug in the appropriate numbers. So my V1 goes in as 2 liters, my T1 is 326 Kelvin, my V2 I don't know, so I'm leaving it V2, and then T2 is 353 Kelvin. To solve this problem, do the crisscross, well not crisscross, the cross multiply. So 2 liters times 353 Kelvin is equal to V2 times 326 Kelvin. Sorry, you shouldn't see any equal sign there. There's parentheses here. So now I have to get V2 by itself. So I'm going to divide by 326 Kelvin on each side. This goes away. V2 equals 2 liters times this temperature divided by that temperature. The Kelvin goes away. And then you know the size of your container after you've increased the temperature. And it's, of course, going to be larger than it was before. Now, if you have any other questions, please see me during tutoring. But how much do they get squeezed and decrease in size? What I'm going to do